This week on Acme School, batteries. Well, gosh. Strictly speaking, these things aren't really batteries. They're cells. This is a battery. It's a 9-volt battery. Inside is a battery of cells. Each cell in the 9-volt battery is 1.5 volts. And the 9-volt battery has a stack of 6 1.5-volt cells. The voltage of a cell is a matter of the irrevocable laws of the universe. It doesn't depend on its size. If you scaled one of these up till it was the size of a house, it would still deliver 1.5 volts. But it would last for a very long time. The voltage is important to the design of a battery-operated device, and the designers will design a unit to operate on 1.5, 3, 4.5, 6 volts, and so on. That's 1, 2, 3, 4, 5 cells, and so on. The amount of power that the unit uses determines the physical size of the cells. A 90-watt boogie box will operate on the tiny AAA cells for a minute or so. Now, cells have been around for about 200 years, and they all have similar components. That is, 2 electrodes of different metals in connection with an electrolyte. I submit to you a brass bathtub and a magnesium rod, the electrodes, and, nothing up my sleeve, salt water, the electrolyte. No one is more amazed than I am when this works. As we say in the science business, ta-da! In case you think I'm getting something for nothing, the energy that's coming from this cell is the energy that was put into the magnesium when it was refined from ore. In other words, this cell works by corroding the magnesium. Cells that used a wet electrolyte like that salt water were the first cells discovered. The most common use today of wet cells is the car battery. Wet cells aren't really too portable. Now, it was possible to make a cell with a paste electrolyte, but since cells work by corroding one of the metals, early dry cells would go dead while they were on the shelf waiting to be used. It was 1888 before the chemistry came along that could give the cell a good shelf life. And that cell would not destroy itself while it was waiting. It was ever ready, so to speak. It occurred to someone that was a pretty good name for the cell. I guess you know the rest. This is the classic carbon cell. Ask me why it's called a carbon cell.
Why is it called a carbon cell? Why is it called a carbon cell?
I don't know. It has a carbon rod in the center, but it's not part of the reaction. The electrodes in a carbon cell are the zinc can that holds everything, and manganese dioxide. The electrolyte is a mixture of ammonium chloride and zinc chloride. It's hard to point all that out because the electrolyte is all mixed in with the manganese dioxide. There's a separating layer of flour and starch near the zinc can if you want the full recipe. The carbon rod runs down the center just as a convenient method of making connection to the paste. It's interesting to note about the carbon cell that it works by corroding its own container. And because plain zinc is the metal that's used, the electrolyte needs to be aggressive, so it's slightly acidic. It's also interesting that if this were a pocket watch, it wouldn't work after I cut it in half, but there's a difference between pocket watches and basic chemistry. You may have seen the mess that an exhausted carbon cell can make. These cells are designed not to leak. Instead, they're designed to die before they corrode their own container all the way through. There is one way to get them to leak, though. Put a dead one in the company of fresh ones. The new ones will force current to flow through the dead one long after it should. That's why cells should always be replaced in sets. The carbon battery is cheap and performs well. Here's a personality profile. Being cold improves its shelf life, which is 1 to 2 years, but it won't work when it's cold. Forget it for emergency car flashlights. It's cheap. I use them in battery-operated radios because it doesn't cost much when you forget to turn them off. It begins to die as soon as you start to use it and goes out on a long, graceful curve, so it won't die without warning, but it's not great for applications that are demanding. It's still my favorite general-purpose cell because of the price. This is the heavy-duty version of the carbon cell. Fancier chemistry, more money, and a slightly different personality. They deliver higher currents longer than the regular zinc carbon cell, and by a nice quirk, the electrolyte gets drier as the cell gets exhausted, lessening the chance of leakage. Heavy-duty carbon cells can be thought of as improved carbon cells. Here's the one you were waiting for, I bet. Alkaline. These cells are radically different from carbon cells, as I found when I sawed one of them in half. The basic dead end in carbon cells is that pesky zinc electrode that has to function as a container. The alkaline cell uses a steel can that isn't involved in the reaction. The electrodes and electrolyte can all be optimized for performance then, and they're powdered and compressed into the can. Compared to the good old carbon cell, the alkaline's upside down in its container. A metal nail makes connection to the paste and it's connected to the bottom of the cell. Now, partly because of the efficient chemistry, the electrolyte doesn't have to be acidic. It's alkaline. This cell is more costly to manufacture, and they pass that on to you. In a lot of applications, though, they're well worth the price. Facts and figures. They'll deliver a heck of a lot of current if they have to. They last longer than any other cells. They have the best shelf life, and they work in the cold. They perform well throughout their entire life, rather than the slow decline of carbon cells. And they're a must for any serious device, like a flash unit. Nickel cadmium, NiCads. They have something special about them that the others don't. The chemical reaction in them is reversible. When they're exhausted, a current can be forced backwards in them to recharge them. They can also deliver the most current of any cell that you or I can buy. And that's all I have nice to say about them. The bad news. They have a shelf life of a couple of months. They're dead when you buy them. That should tell you something. Their cell voltage is not 1.5 like all the others. It's 1.2. You'll find that things designed to use ordinary cells will have slightly reduced performance. They have a memory. If you use them lightly and recharge them often, that's the way they'll start behaving. You have to run them low as often as you can. They die suddenly with very little warning, 30 seconds or so. Don't ever use them in a smoke detector. They take about 10 times longer to charge than to drain. It's not all bad news for NiCads, though. Things that were designed for them work well. There's a whole range of battery-operated stuff that wouldn't even exist if it weren't for nickel-cadmium's rechargeability. Okay. Ask me what's in the button cells.
What's in the button cells?
Everything and anything. Button cells are made with all different chemistries for a lot of different applications. They go by the names of silver, lithium, mercury, alkaline, and air cells. That's why there's such a different array of diameters and thicknesses. That's also why you can never find the ones that fit right. I think I finally got the problem beat, though. I've calculated this D cell should last about 500 years.